Welcome to this video in which we will find the Norton's equivalent circuit for a bridge network. In fact, for the bridge network shown in the picture. Hopefully, you'll recall from the introductory video on the Norton equivalent circuits, we're looking for a circuit that looks like this: a current source in parallel with a resistor. The resistance we call RTH because it's the same as the Thevenin equivalent resistance, and we need to find the short circuit current. So the steps involved in doing this are to find RTH and ISC. We'll find RTH in two ways. The first way is we'll find the open circuit voltage and then the short circuit current, and then RTH is VOC over ISC. And then the other way we'll find it is we'll actually just find the equivalent resistance for RTH. And since we'll have already found ISC, we'll have the Norton equivalent circuit as well. So to begin with, we need to find the open circuit voltage. Okay, so we are finding the Norton equivalent with respect to these two terminals. So the first thing we need to do is find the open circuit voltage across these two terminals. Well, how do we do that, you might ask? Well, you'll notice that we have from here to here 10 volts, and that with the circuit between the terminals open, that I basically have this 350 ohm resistor and this 350 ohm resistor are in series. And so I can use a voltage divider to get the voltage across this resistor here. And in fact, when I do that, let's call this, say, V1. We have V1 is going to be 350 ohms over 350 plus ohms, 350 ohms times 10 volts, which we work out to be 5 volts. The same thing goes for this other branch. Between here and here, I have that the 350 ohm resistor and the 400 ohm resistor are in series. So if I define this voltage here as V2, I have then that V2 will be 400 ohms over 350 ohms plus 400 ohms times 10 volts, which when I calculate this one out, I get that this is 5.33 volts. Okay, and so the way I've defined this, my open circuit voltage is V1 minus V2. That is, the voltage from here to here is the voltage from here to here minus the voltage from here to here. And when I work that out, I get then minus 0.33 volts. Okay, so I've now got the open circuit voltage. Let's see if we can find the short circuit current. This is going to get a bit trickier. Okay, so I bring up a clean version of the circuit, and now I want to short these two terminals and find the short circuit current. Okay, well, how am I going to do that? It turns out that there's a couple things we could do, which I think what we'll do, well, if I knew the current going through this 350 ohm resistor, let's call that I1, And if I knew the current going through this 400 ohm resistor, let's call that I2, then I could apply Kirchhoff's current law to this point, and I would have I1 plus ISC is equal to I2. So if I can figure out what I1 and I2 are, we can solve this equation then for ISC. So the way I think I'll do this is the following. I will come up with an equivalent resistance for the top half of the network, an equivalent resistance for the bottom half of the network, and use those to give me the voltage from here to here. And I guess let's just call this V1. So the idea is we'll solve for the voltage. Everything here is at the same voltage, so we'll solve for that voltage. We'll call it V1. And then once we know what V1 is, we can get I1, because it's going to be 10 volts minus V1 over 350. We can get I2, it's V1 over 400, and that gives us ISC. So I can redraw this circuit to make it clear what I want to do as follows. I have 10 volts, and I have then a 350 ohm resistor, another 350 ohm resistor. These guys are connected. 350 ohms, 400 ohms, and these guys are connected. So what I'm going to do is I'm going to take this resistor and this resistor, put them in parallel, and get an equivalent resistance. I'll then take this resistor and this resistor, put those in parallel, and get an equivalent resistance. And from that I'll have a voltage divider, which gives me V1. Okay, so the 350 in parallel with 350 gives me 175 ohms. If I have two resistances in parallel that have the same resistance, then the equivalent parallel resistance is just half their resistance. 350 in parallel with 400 gives me, this one I'll have to work out, it's going to be 350 times 400 divided by 350 plus 400, which then gives me an equivalent resistance of 186.67 ohms. Okay, so what that means is, well, just to make it clear, this computation here corresponds to these two guys. Okay, so now I can redraw my circuit as the following. I have 10 volts, 175, 180, 6.67. And now I need to find this voltage, which I've called V1. So V1 will be 186.67 over 186.67 plus 175 times 10 volts, which, when I work this guy out, gives me this gives me that V1 is 5.1 5.161 volts. Okay. Knowing this, I can now find I1. It's going to be 10 volts minus 5.161 volts over 350 ohms. And when I compute this, I get a long time to compute this. I get that I1 is equal to 13.83 milliamps. And then I2, here we'll clear out a little bit of space for I2. I2 will be 5.161 volts over 400 ohms, which, when I compute this guy, gives me 12.90 milliamps. Okay, so from this we can compute the short circuit current, ISC, is going to be I2 minus I1, which gives me then 12.9 milliamps minus 13.83 milliamps, which, when I work this guy out, is minus 0.93 milliamps. Okay, so that gives us the short circuit current. How exciting. Now, all we need to do is go back to our original page. We have the open circuit voltage. The short circuit current was minus 0.93 milliamps. The open circuit voltage was, let's do this in the proper color, was minus 0.33 volts. So R Thevenin is minus 0.33 volts divided by minus 0.93 milliamps, which is equal to this is equal to 354.8 ohms. So there we have it. The Norton equivalent circuit here is going to be a current source with negative 0.93 milliamps and a Thevenin equivalent resistance of 354.8 ohms. Okay, so the thing that we haven't done yet is computed the Thevenin equivalence directly by looking at the equivalent resistance of the circuit. And since I'm out of time on this video, we'll do that in the next video.